Okay, physics has a lot of different topics, but the first topic is perhaps the most simple question you can ask, and that is, where is something? So we're going to, this first unit of physics, it's all about describing where things are and at what rate they're changing where they are, and at what rate they're changing the way they're changing where they are. Okay? And where something is called position. How fast or at what rate it's changing its position is called velocity. And the rate at which it's changing its velocity is called acceleration. And these all have very specific definitions that we're gonna go through today. Okay, so let's say here in my classroom, somebody wants to borrow this calculator. And so you're going to tell a friend where this calculator is. Where is it located in space? So and maybe they're in some other, you're going to text message them. You're going to send them a text message to where this calculator is. How are you going to do it? What are you going to send them?
It's on the table.
It's on the table. Well, that's not going to be good enough. Because what do they need to know? Where this table is. And how are they going to know that? Maybe your friend is in another class. So what would you say? It's in Mr. Lake's room. So what are you assuming? That they know where Mr. Lake's room is, right? What if they don't know where Mr. Lake's room is? You could say, well, it's in the Energy Academy in room 902. What if they don't know where the Energy Academy is? Well, start in the main office, walk down, what is that, Molly Lane, and turn right after the big academic building, and then turn left. You could give them directions, but they had to know something before all that. They had to know where the administration building was, right? So if you're going to tell somebody where this thing is, you have to have a place to start. To locate an object in space, you have to have a spot, a location in space where everybody agrees they know where it is. And we have a name for that. It's called the origin. So the origin. So the origin is a location in space where we all agree, hey, we know where that is, and we're going to measure the position of objects in space with respect to that origin. Now, we deal in three-dimensional... Now, and when you give directions, you always have an origin. Okay, when you look at a map, or where somebody gives you directions, if they're going to be effective at all, they always have an origin. That is a starting place, someplace where you know where to begin. And that's why they call it the origin, because it's where you begin. And that's where we're beginning. Now, for right now, we deal in the real world, which has three spatial dimensions that we can observe, right? Supposedly, if you believe in string theory, there's something like 11 spatial dimensions, but 8 of them are all folded in on themselves, and so we don't really observe them, if that's really true. But we know, for practical purposes, that here's my calculator, and my calculator, I can move it left and right. I can move it, like this, or I can go like that. Okay, so there's 3 spatial dimensions. Okay, north, south, east, west, and up, down, and they're all perpendicular to each other. Each one of those dimensions. But we're going to start off doing something really simple, and that is we're only going to deal with one dimension at a time. Single dimensional motion. And So if you go to a movie, you see a 2D movie. If you see 3D movie, okay, they trick your brain into thinking. Imagine how boring a 1D movie would be. It would just be a line across the screen. So they're not very popular, but they are very simple, and that's where we're going to start. So to locate where an object is in space, you need, on a single dimension, you need to know what is your single dimension. And we'll call this the x-axis. Okay? Or it could be the y or the z-axis. Those are the standard letters we use, x, y, and z, for the 3 dimensions of space. And let's say my calculator is located right here. Here's my calculator. Okay. And here's the origin over here. So what we're going to do is we're going to measure the position of the calculator. Now, what is position? Position is the location of an object in space as measured from the origin. So the calculator, you might say it's 1, 2, 3, 4, 5. And we'll just do this in meters. So 1, 2, 3, 4, 5. So on my imaginary calculator, I could say, oh, well, if here's the origin and here's my x-axis, my calculator has a position of 3 meters. So this is an operational definition. I am defining position here as a procedure to follow. So what I mean when I say position is I mean where an object is as measured from an origin. Okay, and it has units of length, meters, or centimeters, miles, parsecs, whatever you want to use, but that's where it is. Okay, position. Now, suppose that I put wheels on my calculator and it's moving. And let's say my calculator, I look at my calculator, a little time interval goes by, and my calculator is now, it's walked all the way over here. So now my calculator has a different position. So my calculator over time has changed its position. Okay. So this was its initial position, and let's say this is its final position. So it went from here to here. So I have a way of expressing position as a variable. I'm just going to call it x. So I could say x initial equals 3 meters. So that little subscript I, you've seen this many times before, that just means where it was at the beginning of my time interval, or the time that I'm looking at. It took time for it to move from here to here. Objects cannot move instantaneously from one position to another position. It always takes time, to change your position. And so I can say x final, the final position is equal to 5 meters. Now, one thing about position is a kind of quantity that is, we call it a vector quantity. I know in math, in AMA, I taught AMA for a while, you learned about vectors, but I think we'll just review them very briefly. A vector quantity is a quantity where in order to express that quantity, you need to give a magnitude and a direction. Okay? So a magnitude and a direction. So x initial equals 3 meters. That has a magnitude, but what about the direction? Well, let's draw it as an arrow. Anything that can be represented with an arrow can be thought of as a vector. So here's my initial position. So this is my initial position vector. And it's an arrow, and here's where you start. That's the tail of the arrow. It goes out here. So there's my initial position. Now my final position, I'll just stack the arrows, okay, just to make it easier to look at. I'll just stack the final position on top up here. there's my final position vector. Okay, now vectors, when you draw an arrow, it's got a, I'll call this the point or the head of the arrow. This is the tail of it. So you go the tail. When you're dealing with position vectors, the tail of the arrow you're going to represent it with is always on the origin. Position, by definition, is measured from the origin to the location in space where your object is located. Okay, so from here out to there, from here to here. Okay, now what about direction? Well, here's the thing. What if I had an object located over here? So 1 meter, 2 meters. What if my calculator was over here? What would that position be? Well, you need a way of saying, oh, look. If I just say, okay, x, if I just said x equals 2 meters, well, that's sort of true. I am 2 meters away from the origin, but there's another place on the axis that's 2 meters from the origin, right? Over here. I'm sorry, I didn't draw those to scale because I ran out of room on the paper. But there's a real easy way of saying which direction it's in. What's that real easy way, do you think? Yeah, positive and negative. So I'm going to say it's located at negative 2 meters. Now, when you're dealing with a scalar, a negative quite often means you have taken a certain quantity away, okay, or you have a debt, or you lack something. With a vector, that's not what negative means. Negative just means in the opposite direction of positive. So you choose what's positive, usually on a horizontal axis. It's just by convention. To the right is positive, and to the left is negative. So when you see this x equals negative 2 meters, 2 meters is the magnitude, that is how far away from the origin that position is, and the negative means to the left. So you've identified the direction, and you've identified the magnitude. The vector is complete. The position vector is complete. Okay? Now, let's forget about this for a second, and let's just deal with these. Notice that my calculator, as I moved it, it changed positions, didn't it? It went from here to here. So we have a change in position. Well, we have a symbol that stands for a change in any quantity, right? Delta. And position, the variable we're using to represent position, is x. Now, by how much did this calculator change its position? By 2 meters. So we know just by looking at it that it's 2 meters. But, and what did we do? How did we get 2 meters? Well, we started at 3 and we went to 5, and you can just count, right? You can just count 1, 2 meters. In what direction? To the right, which means it is positive, okay? But what if you don't want to count? There's a little, I mean, with these numbers it's easy, but what if I had, like, the initial position was 243 meters and the final position was 6,127 meters? You would not want to count. So what would you do? You would subtract, right? You would say, well, my final position was 5 meters. My initial position was 3 meters, so I changed by positive 2. So I go, well, 5 minus 3 is 2 meters. So we have an operational definition for a change in position. Delta x, by definition, okay. Have you seen this equal sign before where there's 3? Have you seen it before? Okay, if you've never seen it before, this is a mathematical shortcut for saying, hey, delta x is not only equal to the final position minus the initial position, delta x is defined to be the final position minus the initial position. So this isn't saying delta x is equal to this. It's saying delta x is defined to be this. All right, it's even more than equal. It's like defined. All right. So now this has a name. This change in position has a name. It's also known in physics. It's called displacement. So the displacement of the object is the final position minus the initial position. Now, by the way, displacements can be negative. What if I used this as my final position and the 5 meters as my initial position? Suppose that I went from here to here. Well, I'd need to draw an arrow, right, from my initial position to, oh, I forgot to do that. You can make the displacement is a vector. You can draw it. And the tail of the vector starts where the object started and ends at the final position. So the tail at the initial position, the head at the final position. Well, what if this was my initial position and I move the calculator over here? Well, I draw an arrow like this, right? So delta x would be the final position, which is, oops, -2. Am I still on screen? Okay. Yeah. -2 meters minus the initial position. That's minus 5 meters, right? So what is -2 minus 5? -7. -7 meters is my displacement if I go from here to here. Does that make sense? Yes. What does the negative mean? To the left. This is a vector quantity, so the negative defines a direction. And how far to the left? Well, we moved 7 meters. So this is kind of interesting. The magnitude of the displacement was greater than the magnitudes of the positions. Perfectly okay for that to be. All right. Now, there is one other definition. Let's say that the car started here, went here, and then went here. So, or the car, I'm sorry, I'm using a calculator because that's what I put under the video camera here. But let's say that I had an object, some object, and I started here, I moved here, and then I moved here. Now for that total time interval, for that whole set of motion, I started here, and I went whoop, whoop. What was my displacement? 5 meters? Yes, it does. Oh, okay. Yeah, you can displace to the right or you can displace to the left. So the displacement has a direction. So we would say, well, in that case, if I start here and go over here to here, I can say, well, delta x, well, I started here and I go 1, 2, 3, 4, 5 meters to the left. So I can say, well, delta x in that case is equal to -5 meters. But let's be official about it. What's the final position? -2 meters. What was my initial position? 3 minus 3 meters. So the final position minus the initial position gives me -5 meters. Okay. Now, what distance did the calculator travel in this little path that I've come up with? Okay. Distance. Okay, now this has an operational definition. Distance. So distance is just the length of the path traveled. Now, that's the definition of distance. So let's take a look at the length of the path traveled. And distance, by this definition, distance is not a vector. It's just totally magnitude, and you're just adding up. There's no such thing as a negative distance. Yes, there is such a thing as a negative position, because the negative just means to the left. There is such a thing as a negative displacement. It just means you go to the left. But distance, Let's start here, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I start here and go over here and then move back here, my total distance was 9. meters. So I'm just going to use the letter D for distance. My distance was 9 meters. Oops. By the way, if I ever am writing and I go off screen, let me know. Please let me know. Let me zoom out a little bit, give myself some more room. Okay, well, it took time for this object to move from here to here, or from here to here to here, or whatever. So what I can do is I can define I can give an idea of how fast something is moving. I mean, if something has a displacement in very little time, that means it's going really fast. If something has a displacement that took a long time, that means it's moving slowly. So we need some way of dealing with that. And we're going to look at it in several different ways. We're going to look at it graphically here pretty soon. But we're going to define a new quantity here, and that is average velocity. Now, if you took regular physics, we did a whole lab to derive what average velocity is. You might remember the buggy car lab and all that. But unfortunately, in this class, we have to move so fast that I'm just going to get to the point. But it's pretty. I think it's pretty easy. Average velocity, which I'm going to put a little. Well, here's how I'm going to write this down. I'm going to put a V. A cursive V is what we usually use for any kind of velocity. Now, velocity is a vector quantity. So to show that it's a vector, I put a little arrow on top of it. But I don't show the whole arrow. I just show that I could draw the whole arrow if I want, like that. And a lot of people actually write vectors like that. But I was taught just to go, okay, V like that. That's the way you say, okay, see this little symbol right here? It just means, hey, this variable, this quantity, it's a scalar quantity, so deal with it. It's got direction. Okay, that's what it means. So delta x by definition. Oh, and by the way, this is average velocity. So I'm going to do this a little different than the book. I'm going to put a AVG. Here's what the book does. The book does a boldface. Now, what the book does is it uses, if a variable is, or if a quantity is a vector, they make it boldface. And then if it's not in boldface, it's not a vector, or it's the magnitude of a vector. But I don't want to have to write in boldface because it's too awkward. So that's why I use the little arrow over the quantity. But what they do is they put a little bar, and I don't know if in your math class, did you ever use a little bar like that to mean an average? Like maybe in stats or something. But in the book, they use a little bar over this boldface V to mean average velocity. Okay. So by definition, average velocity is delta x over delta t. It's the rate. You take the total displacement and divide it by the time it takes to make that total displacement, and you got it. Okay. Okay. So this is a definition, and this is a definition right here, a mathematical definition. And by the way, origin, position, displacement, average velocity, distance, these are terms you need to know. Okay, so if you need to make a vocabulary list or note cards or whatever, there's not a ton of vocabulary in physics. That's the nice thing about physics, is it's just not that much to know. Okay, compared to like AP Bio or something, which is insane. All right. So there's your average velocity. Now, let me show you an object that's in motion Oh, before I get to that. Now, let's take a look at this object up here, like the example that we did. Let's say that it moved from here to here over to here, that whole trip that I drew here. Started at 3, went to 5, then went to -2. And let's say that took 5 seconds to do. So delta t, the calculator, I was moving it, I moved it like this, and I moved it like this. You have to follow this definition. So what was the average velocity for the calculator? Well, in this example, the displacement was -5, right? If I end at -2 and I started at 3, I went -5 meters. And if it took 5 seconds, so, well, that's pretty easy. 5 divided by 5 is 1, but it's -1. -1 meters per second. Now, what that means is that even though I zigzagged, it's as if going from here to here in 5 seconds is as if I'm going like 1 meter per second. It has the same effect. Okay? So that's what average velocity means there. Now, we also have this thing called average speed. And there is no variable for average speed that I know of. So I'm just going to like write speed. I'll just write the word out. And by definition, average speed is total distance over total time, right? So total distance over total time. Well, for the example I'm using, what's the total distance I traveled? 9 meters. So this is going to be equal to 9 meters divided by 5 seconds. So what is that, 1.8, I think? 9 divided by 5, I believe, is 1.8 meters per second. Now, think about this. Average speed can never be negative because you can't have a time interval that's negative. You can't go back in time. And there's no such thing as negative distance. So you have a positive divided by a positive. What does the negative mean here for average velocity, though? It just means direction. And velocity has a direction, speed doesn't. And notice that the answers are different because they mean different things. Now, in the Indianapolis 500, okay, you've all heard of that race? The finish line is also the starting line. So by these definitions, what is the average velocity of the winning car of the Indianapolis 500? It's 0. It has a 0 average velocity. So does it make sense to use average velocity in that context? No. But it goes, let's say it takes, the winning car goes 500 miles in, I don't know, what, 3 hours? So what's 500 divided by 3? I can't do it in my head. 100 and a lot. Like 180 or something. So the average speed of the winning car, the Indianapolis 500, is pretty close to 200 miles an hour. A little less than 200 miles an hour. Does that make sense? Yes. So whether you use average speed or average velocity, whether you use distance or displacement, it depends on what the situation is. You have to understand what these things mean in order to use them properly. Okay. Now, we have another kind of velocity, and that is called instantaneous velocity. And this quantity is well named. Instantaneous velocity. It means how fast and in what direction you're going right now. Not over a time interval, but right now. Now you have an instantaneous velocity machine in your car. It's called a speedometer. Now actually the speedometer gives you the instantaneous speed, but just point your finger in the direction you're going and now you got the direction along with that speed, so you've got your instantaneous velocity. Okay, as long as you point your finger in the direction you're going. So instantaneous velocity is how fast you're going at an instant in time. It is a vector, and it has a definition. And since all of you have had at least a little bit of differential calculus, we're just going to go right to that definition. We will reinforce it later on. But it's delta x over delta t. But what am I going to do with delta t? I'm going to take the limit as delta t goes to 0. And that's, or this also is called dx dt. Now we are going on, next time we're actually going to study differential calculus. I'm going to give a lecture on it so that those of you who only had AMA, have only had AMA so far, and actually some of you may have had AM and you didn't have any derivatives at all, and maybe you're in Calc AB this year, in which case this first part is going to be a little bit of a struggle. Not a big deal. Not that big a deal, because you're going to get it very soon in your math class. And it's not a big deal on the test. But in any case, this is the operational definition. And oh, by the way, I don't put vector hats on delta x's very often because it's kind of in the x direction, either negative or positive, so it's kind of redundant to put the vector hat on it, but you can put the vector hat on those variables. Now, here's what I'm going to do. I'm going to draw a graph of an object that's moving through time. So I'm going to flip my x-axis and I'm going to make it look like this. So 0, 1, 2, 3, 4, 5, 6. Okay, and so this is in meters, so this is the x-axis in meters. This is my position axis. Now, here's what we're going to do. I'm going to have my car, I'm going to have a little car right here, and it's going to start right here at 2 meters, and it's going to do this. It's going to go, okay. It's just going to drive. It's like you're going like this, and you go, oh, wait, no, I'm going to go this way. Then what I'm going to do for that motion, I'm going to graph it over time. So this is my time axis in seconds. And maybe this will take 5 or 6 seconds. So what I do is I say, okay, at 0 time, where is my little car? Well, it's right here. And at 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. What is it doing? Well, it's going to go like that. So what I'm doing is I'm taking this one-dimensional motion, okay, little car starting here, and it starts at rest, and it increases in velocity, and then it's got to stop, and it's got to change its direction and go backwards. So it goes backwards, and then it speeds up, and then it slows down again and stops at right there. And it took 5 seconds. This is a position versus time graph. Okay? And so I can look at average velocities. I can look at instantaneous velocities on here. And So this is one of the things that they do in the book really well. So definitely, read the book as well as doing this. But let's say, what's the average velocity? What's the average between, let's say, between 1 second and to 3 seconds? What's my average velocity there? Just looking at this graph. All right. Well, at 1 second. There I am at 1 second. Looks like I'm at 3 meters, roughly. So what is this? What is this 3 meters? For this, from 1 second to 3 seconds. That's my initial position from the time interval I'm looking at. See, let's say 3 seconds. Where am I at 3 seconds? Oh, it looks like, I kind of did that almost like I planned it this way. I didn't, but, that's almost too good. Oh, well, we'll just go with it. I'm just too good. All right, the average velocity here is, well, what's my final position for this time interval from 1 second to 3 seconds? It's, my final position is 5 meters minus my initial position, which was 3 meters. The initial position for the time interval I'm looking at, not from 0, but from 1 second. Now, remember, my definition is delta x over delta t. So what is delta t here? Well, it had a final, remember, anytime you have a delta, it's a final minus an initial, right? So it had a final time of 3 seconds minus an initial time of 1 second. So what is that? Oh, it's 2 meters divided by 2 seconds. That's why it's too good. I didn't want it to be that good. Oh, what is that? That's 1 meter per second. Another way of looking at this on the graph, though, is this is the slope of the line that connects these 2 points on the graph. Now, what if I want to know what is the instantaneous velocity at 1 second? What's the instantaneous velocity at 1 second? Well, here's what I can do. Here's my delta t, right? 3 seconds. What I can do to this delta t is I can let it shrink to 0, so that what you get is a tangent line. Do you remember this from your math class, that the instantaneous, the derivative is the slope of the tangent line? We're going to cover this on Thursday, but that's what's going on here. So now what I could do is draw the tangent line, pick 2 points on the tangent line, and figure out what the slope is, and that'll be the instantaneous velocity at 1 second. Or you can just get your pencil out and just make little tangent lines, and the slope of these tangent lines is the instantaneous velocity as you move along. Okay? But that's all the time I've got for right now. My time interval has expired. So, but I think you've got enough information to do the homework. So, or the class, or the assignment. So, assignment 1, the examples, the questions, the problems are due tomorrow. I will check them to make sure that they've been done. So give them a good attempt. That is all.